Today we want to go over the hemispherical pool with water in it. The pool has a radius of 4 meters and it contains water to a depth of 2 meters. Tomorrow I'm going to ask you to write a triple integral for the volume of the water in the pool in rectangular coordinates, and then you're going to get to choose spherical or cylindrical coordinates for the second part. We start by writing with the equation for the whole sphere with a radius of 4 meters. That's x squared plus y squared plus z squared equals 4 squared. We need x, y, and z because we're in R3. If we were in R4, we just need our fourth one. They'd all square, sum them up, radius squared. I want the bottom part of the sphere, so I'm going to take z equals negative square root of 16 minus x squared minus y squared. This is the bottom of the water. The top of the water will be the depth of -2. This is the integral. This will be the interval over which we integrate dz. Since we're writing z in terms of x and y, that tells us that the z is going to have to go first. That's going to have to be our first integral, our innermost integral. So when I set up my integral, let's see, I want the volume, so I'm just gonna write the generic function first. If I want z to start off at negative square root of 16 minus x squared minus y squared and stop at -2, I have to set dz up as the first integral. I have to integrate dz first because we've written z in terms of x and y. Early integrals can be functions of upcoming variables. The last integral has to be constants. For the dx and dy, I can look at what's going on from above. From above, here is the top of the pool, but we're interested in the surface of the water. Here are the x and y values that we're interested in. We need to know the radius of the circle representing the surface of the water. We need to know the radius of the circle that is the top of the water. It's x squared plus y squared equals some radius squared. We have to figure out what that is. What we know is that at this circle, z is equal to -2. So the top of the water is when z is equal to -2. And z is also negative square root of 16 minus x squared plus y squared. This has x and y in it, but we're trying to solve for the x squared plus y squared. That's the only part we need. I need to know what x squared plus y squared equals r squared. So Change the sign and square both sides. And so 4 is equal to 16 minus x squared plus y squared. And so x squared plus y squared is equal to 12. This is the part where you have to know that by truncating the hemisphere at a depth of 2 meters, at a depth of 2 meters, does not make a hemisphere. So the radius of that circle that represents the top of the water is not 2. The radius there is the square root of 12. Any questions? Is everybody okay? Everybody looks shocked. You all look like this. I think you're mad because I'm telling you what the problem is tomorrow. Oh, dude, you ruined the surprise. How about a spoiler alert next time? Surprises are overrated. So, the problem with just trying to surprise you with this is that this is the square root of 12. That becomes the focus of the problem. Then it stops being about setting up a triple integral, and it just becomes an old geometry problem. And it feels bad when you ask that question. Just so for those of you who are like future calculus teachers, they're like, oh yeah, I'm going to fill it halfway too. And that way they'll think it's the circle is a radius of 2. You're being a dick when you do that. It's not cool. It's not funny. You're not being clever. If you set a trap for your students and then the students fall into it. That makes sense? Incidentally, when the teacher sets a trap for you and you fall into it, that is what you're supposed to do because you're the fucking heroes. That's what heroes do. Batman's like, oh, this is a trap, Robin. Robin's like, oh, are we going to go around it? It's like, oh, no, we're going to walk right into it because that's what heroes do. We walk into the trap and use our wits to escape. You know what I mean? So I don't want you to fall for this trap. It's a square root of 12, not 2. But then now the problem's all over. Now I can describe what y is between and then say what x is between. So what's y between? The two paths that we can take is we can either solve this for what's y between by saying y is plus or minus the square root of 12 minus x squared. So y is the bottom circle up to the top circle for x between negative root 12 and root 12. Or if we don't want to do a dy dx, we could do a dx dy and say x is plus or minus the square root of 12 minus y squared for y between negative root 12 and root 12. So those are your two choices. I would probably pick dy and say this goes from negative square root of 12 minus x squared to positive square root of 12 minus x squared. And then dx from negative root 12 to root 12. I would probably even put a plus on this one just to make sure. Now notice that this represents the bottom and the top of the circle from the top view. So this part of the circle and this part of the circle. And then the negative root 12 to root 12 is from left to right from this top view. In other cases, we have to think about where we're truncating things. We have to think about where we truncated that 2 meters. The 2 meters of water was represented in the Z. That's where we truncated things. That Z equals -2 gives us that bottom 2 meters. If I wanted the whole hemisphere, the volume of the entire hemisphere, we would do 2/3 pi r cubed because we have that one already. But in the triple integral form, we would go from negative square roots up to 0. The -2 up to 0 is the space that's not filled in. Any questions? Yes. So I wrote, the reason I did dz as my first is that I know that z is going to be easiest to express in terms of x and y. Since I'm writing z as a function of x and y, I need to have x and y the upcoming variables. So since the z is in terms of x and y, I've got to do that one first so that I can have the dy and dx integrals after it. They have to come after since I'm using that as part of my expression. The other thing is that I've chosen, in this setup, I've chosen the z to be the vertical axis. So that's where the water is, from z equals -4 to z equals -2. That was an arbitrary choice, but typical. If you want to be different, if you don't want to be one of those Brittany and Justin wannabes, then you can totally have gravity go sideways. Say, no, that's the y-axis. And I know it's going off in that direction, but you can say, oh, that's positive now. Or you could set it up this way and make that the positive direction, or that the negative direction, and go from the positive square root to +2. You have options. So good news, you have options. Bad news, you have options. We all think we want choices until we have to make choices. This is the typical way to set up the problem, and it just barely doesn't fit. It's one line away from, oh man, hold on, let's put that part on. Any questions? Yes. Uh-huh. Yes, for spherical coordinates, one of the problems that we have in this problem, one of the difficult things about this problem is that the surface of the water is flat, and spherical coordinates do not like flat things like that. So we would have to come up with a solution for that. If we were to use cylindrical coordinates, then the z that we're using would almost work. The only problem is that z is in terms of x and y, and I would need to write z in terms of r and theta. Of the two, which would be easier? I know this is a hemispherical pool of water. Hemispherical pool of water. So which set of coordinates would be easier to write a triple integral? Spherical or cylindrical? I'm leaning into spherical really hard, aren't I? That would be way worse. Why is spherical way worse in this scenario? Oh, spherical coordinates would be kind of a pain in the butt in this problem. For what reason? Because of this right here, this place where z is equal to -2. Where z is equal to that z equals -2, that flat plane that is not the xy plane, that's a problem. Because the only thing that we have for distance is rho. I can't remember what color I was using for rho. So here, rho is 2, but then rho, based on some different angles of phi, has to go from 2 out to the square root of 12. At least we know it's at the square root of 12. But those values of rho are variable. Theta would be easy because theta is just going all the way around. That goes from 0 to 2 pi. But I would need the values of rho that go from here down to pi. Yeah, that would be the same problem that we did yesterday, where z is equal to rho times the sine of, or cosine. The reason I would like cylindrical coordinates for this is that I set this problem up with a z in it already. It's like, oh, dude, you've already got the z in there. You just have to rewrite your z in terms of r and theta instead of x and y. Any questions? Comments? Snide remarks? How's everybody okay? I told you count 3 was the easier one. Was that? Yeah, I would personally do cylindrical. The main reason I would do cylindrical is that z is written in terms of x and y, but the form of z has an x squared plus y squared in it. And what can I do with x squared plus y squared? What do I replace that with? If cylindrical coordinates is just polar coordinates with a z-axis. And the relationship between rectangular and polar coordinates says x squared plus y squared equals r squared. So where we had before z is equal to negative square roots of 16 minus x squared plus y squared. In cylindrical coordinates, we would write negative square roots of 16 minus r squared. Then we just need the values of r. R goes from 0 out to the radius of this circle, which we had previously calculated as square root of 12. So r goes from 0 to square root of 12. And theta goes all the way around. So theta just goes from 0 to 2 pi. Any questions? So the sneaky part of this problem is to set things up in a sphere to try to, first of all, trick you into making this, the radius of this circle 2 instead of square root of 12. That's trick number 1. Trick number 2 is to say it's spherical. Wouldn't you like to use spherical coordinates? But no, because stuff is the same going around this way. We're going to exploit this symmetry, and we care about changes in depth. And we've got this big flat plane where z is equal to -2. And it's really easy to write a formula function for z. It's kind of a complicated function to write for rho. Everybody okay? Any questions? Comments? Any thoughts? So there's some advanced intel on the problem that you'll be facing tomorrow. I have a selection of problems to put on the double integral side of the paper. It's just writing integrals. Mm-mm. That would be too much calculus to ask you to do actually calculate the integrals. If someone would set something up with rectangular coordinates, and there's going to be a square root of 4 minus x squared. All right, I'll do some trigonometric substitution. Then you have to turn in the test and you're still in the trigonometric substitution. So tomorrow, just setting up double integrals on the first page, setting up a couple of triple integrals on the second page. It is a hemispherical pool of water. I did not change the 4. I did not change the 2. It's 4 meters and 2 meters. There's some advanced intel. You get a lot of extra advanced intel if I'm behind on my grading. That's just kind of the way it goes. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day. Thanks for playing.